you what, since I haven't entered the grades yet, but once I enter those grades, we're not taking it anymore. So it's only example. Hey, Lily. Lily, what transformation is this minus sign here? Sandra, enough, enough, enough. Can't hear it anymore. You guys, so this is what we're talking about from Friday. This is the graph that we created Friday. Y equals the square root of x. I said, I'd really love for you to understand how to make it without looking at decimals, thinking about just integers. So, this is the y equals the square root of x. Now, if we put a negative sign in front, it's going to reflect it across the x-axis. It's going to flip it down. All right, thank you. Let's do another one. What about this plus 2 underneath the radical bar? What effect will that plus 2 have on the graph? Okay. Yeah, that's actually going to go left 2 units. A horizontal translation of negative 2. Now, what about that plus 3 there, Dylan? Vertical translation of 3. That's going to be up 3. So I have this graph is flipped left and up. 3 moves. All right, so I'm going to help you make a table. Dive right in if you got it, but I'm going to make a table here. There's a lot of different ways to understand this table, but we'll break down one way right now. So here's the parent function table. I said that the best numbers to square root are 0, 1, 4, 9, 4 square roots, and 9 square roots. So I like those in this table. But with this 2 here, it changes everything. Because if I put a 4 here, I have the square root of 6, and that's a decimal, and I really want to try to make a table that doesn't need decimals. So I'm hoping to create the square root of 0, and the square root of 1, and the square root of 4, and the square root of 9. So what number could I put here to give me a 0 under the radical? How could I create the square root of 0? Ryan? Negative 2 will do it. This time, instead of starting with 0, I'm starting with negative 2. Let's see if that really works. See if Ryan really knows what he's talking about. So this is negative 1, and I'm going to put negative 2 in the x spot. So the order of operations here is that I do this under the radical bar first. That's actually considered a grouping symbol, like parentheses. Oh, there it is. There's the square root of 0. So that's negative 1 times 0 plus 3. So that's 0 plus 3. So that's 3. So my first ordered pair is negative 2, comma 3. All right, how do I create the square root of 1? So So just like I ended up with this 0 here, I want to do that again, but I want to have a 1 underneath there. What number would I put so that I have a 1 here? -1 goes next. Let's just keep going. What would I have to do to have a 4 under here? What number for x would give me a 4? 2. And somebody else, what number under there would give me a 9? Tristan. 7. Suzanne, did you make a table? No? Can I ask you, if I was to compare these x's to these x's, how are they different? What's the pattern? Yeah, subtract 2. Which I can see here. I said left 2, so in order to go left 2, I have to subtract 2 from all of these. Like 9 minus 2 is the 7. 4 minus 2 is the 2. 1 minus 2 is the -1, and 0 minus 2 is the -2. So, and truly understanding your transformations. You subtract 2 from x values. That might help you understand the left instead of right. You know? -1 times -1 plus 2 plus 1 times square root of 1 plus square. Remember. -1 times square root 2 plus 2 plus 3. -1 times square root 4 plus 3. -2 plus 3, 1. -1 times the square root of 7 plus 2 plus 3. -2 plus 3 is zero? Zero. Alright. So here's our ordered pairs. I have -2, comma 3, -1, comma 2, 2, comma 1, and 7, comma 0. Okay. There it is. Flipped over, left 2, up 3. Yeah, let me go back to the problems. So, this is what we're doing right now. Describe the transformation with words. Number 2 is to drop them. And number 3 is to give domain and range. So I'll take a moment of pause. Give domain and range. Directions for number 2 is to graph both F and G. Go ahead, Kelly. Daisy, how'd you do? Did you come up with anything? Daisy, you gonna domain? Daisy, can you? Madison, can you do domain and range? Let's hear it. Yeah, so our x values, like if we focus on the x-axis, the endpoint is at where x is -2, so we can't go any further left than -2. So I'm going to write that as x is greater than or equal to -2. And what's the range? All right, focus on the y-axis. Madison, what value did you put in for range? 3. On the y-axis, the endpoint's at 3. It doesn't go any higher than 3. So this is y is less than or equal to 3. So when you wrote down transformations Friday, I said that this is the domain and this number's the range. And this is opposite. So it's a +2, but I actually use a -2. It's going left. Got 3 and landed right in my range column. Alright, when you're ready, get out your docs from Friday. I'll give you credit for doing them. I didn't show you 17 yet, I don't think.
Song from Prison. You're not trying to cut up.
Look at it, it was done. Nice. Yeah. It's old. Oh, I did not do it. It's not done here. It's not. Very nice. You want to show me the day before? The day before. I don't know. There was a quiz, and then I said when you're done, try to graph the square root of x. Then you can Google it. Very good. Very good. No, not yet. Gabe, where's your graphs? Where's your graphs?
No, these, all of us.
Thank you.
It's all good.
Thank you. I got you. Thank you. Okay, thank you. Alright, so now I'll show you the answers to 32, 33, 34. Lots of people didn't do it because it wasn't done in class. Alright, take a look. It says, and it's multiple choice. So this is, I mean, I would consider this a very easy SAT question. I mean, not because I think the concept is all that easy, but because you don't actually have to do any math for it, right? It would be a no calculator type question. So this graph is right 12. Well, right 12, I typically think of plus 12. So somebody with no algebra 2 is going to pick either, they'll probably pick C, plus 12. There's 12s all over the place. This is to the right. So somebody with no background math on this topic would probably pick C. But I know I'm looking for the opposite. So I'm actually searching for negative 12, this one. And that's because if I put a positive 12 for x in here, 12 minus 12 is 0, the square root of 0 is 0, and that y value is 0. So that ordered pair matches that equation. Think about it. All right, a reflection across x just means put a negative sign in the front. And 4 units down means take your 7, which is in the k spot, and subtract 4. So I need to see a 3 there. 4 units down leaves you at 3. All right, today we are starting chapter 5.4, which is all about the cube root function. So you're going to take notes on this whiteboard. I want you to come up with a table of x values that you can plug in if we have a cube root instead of a square root. So what can I put in? I want specific x values that will not have decimals. So now you have to think about different numbers that square root are not the same as numbers that cube root. Put your phone away. Okay. What did you put, Sandra? What is it? No interest in that? Thank you. I already have that knowledge in my mind. I don't need paperwork for it. Whoa. That's, there's no profanity.
I don't have this page. I looked at my book and it's ripped out, but it's not here.
Have you looked in your folder?
Probably find it.
My goodness. What, Anton? You must be done. What cube roots, Anton? Yeah, like what's a good number that I can cube root without a decimal? Eight's in the list. Eight's in the list. How'd you come up with 8? Dang, 8's in the list. What's the cube root of 8? 2. I'm gonna put 8 like right here. Boom. 8's in the list. The cube root of 8 is 2. Okay, what else is in the list? Adrian, Ben. 0 cube roots. What's the cube root of 0? Yeah, 0's always there. What else cube roots? Madison. 1. 1 always cube roots. What's the cube root of 10?
No, I mean, I changed my answer from 10 to 16.
What's the cube root of 16? I don't know.
It's 4 times 4.
Yeah, that's a square root though, but I want to know 4 times 4 times 4. We're cubing.
4 times 4 times 4. 4 times 4 times 4. 64.
We could put 27 in our list. The cube root of 27 is 3. We can put 64 in our list because we are cube rooting. We are not square rooting. The cube root of 64 is 4. Click it. -1. Can you cube root a negative? Yes, you can. So Friday I said don't put negatives. The square root of negative is not a real number. I can't graph it. But today I say yes. Green light, go on negatives. You can cube root a negative. So for the cube root table, you include negatives. Wow, moving from a square root right to a cube root, that's going to help me understand things a little bit. Anton, do you want to stand up, walk your phone to my desk? You can. I don't mind. I don't mind doing that. Yeah, 5. Yeah, you should write this. I'm going to go ahead and do one other negative. Yeah, 216 too. What's the cube root of -8? Okay, that's -8 cubed. Yeah. What's -2 times -2 times -2? Yeah, that's what I was looking for. Alright guys, go ahead and graph this. Let's see what this picture looks like. Hey guys, let's just do these first 5 points. 27 is kind of hard to get to, and so is 64, so let's go through -8 to +8. Plot your points to see what it looks like. Yeah. You think so? So let's talk about how this compares to the parent square root function. Tell me a significant this point forward, they kind of look pretty similar, but this one gets to keep going. So for that reason, I find this one less interesting than this one. This one has an endpoint that's kind of like, ooh, what's going on with you? But that one just kind of goes both ways. Whatever. So this one, since it goes both ways, has like that same old boring domain of all real numbers. And it has the same old boring range of all real numbers. So, boring, yes. Now I'd like for a minute to try to get you to remember before winter break. We were working on polynomials, with like x to the third and x to the fifth, like odd degree polynomials versus even degree polynomials. You guys remember talking about end behavior where the arrows go the same way and arrows go opposite ways? Well, x to the third looks like this. If I added more to it, it could have two terms, but it would start long and high. Y equals x to the third in its most basic state has a table like this: -2, -2 to the third power is -8, -1 to the third power is -1, 0, 1, 2. If you look, this is the exact shape as that one. They are congruent. They're the same shape. That one just is actually reflected diagonal. It's a diagonal reflection. So x and y are perfectly switched. That creates a reflection. Instead of up or down, it actually flips like a 90-degree flip. So these are inverses. X to the third and the cube root of x, they're perfect inverses. They have the same shape. They're just going different directions. So if you can understand this one, it should help you understand that one a little bit. Just the x and y are switched. All of the same transformations that we talked about square roots apply to cube roots and every root for that matter. If there's a negative, it's a reflection, stretches and shrinks. If there's a number here, it shifts it right, left, opposite. A number here moves it up, down, opposite. So here's cube roots. Pretty much exactly what you did Friday, but this time it's cube roots and not square roots.